Alberta. And it's my pleasure to welcome Brandon Basso to MIT to give the seminar. Brandon finished his PhD with Carl Hendrick in 2010 at UC Berkeley, and we're doing work in multi-area coordination. And one of the things that I remember about when he visited at that time was that he did a lot of work flying outdoors and actually making real things work. And after that, Brandon went to 3D robotics. And for those of you who don't know, 3D robotics was one of the big three of consumer small-scale UAVs in the world. The 3D Iris is one of the best-selling UAVs you can buy. And I'm really happy to have Brandon here to talk to us about the work that they've been doing in sort of advancing the state-of-the-art of these vehicles, the state-of-the-art of unmanned air vehicle technology. And I'm sure if any of you are graduating soon and want to talk to Brandon about 3DR, he'll welcome him to chat with you. So with that, Brandon.
Thanks very much, Nick. It's love being here in sunny Boston. Thanks for having me out. It's fantastic weather. It doesn't hold a candle to California. So I'm going to cover a couple topics today, give a little bit of an overview of 3DR for those of you who don't know about it. It's a fairly unique company. Most of what we produce is open source, for example, software-wise. And I'm going to talk a little bit about this idea of this open UAV platform, which is, I think, very important for academia, very important for industries. If you guys monitor Kickstarter, you probably see all these aircraft out there that are building applications. A lot of students from MIT actually that are doing that, building all sorts of hardware and software things on top of a UAV platform. Most of the time, it's a 3DR platform. So, brief outline, I'll talk about where 3DR is today and a little bit about how we got here as the history's importance. Oh, I'm on the wrong slide. I'll talk in some amount of detail about work that we've done. Probably the biggest technological improvements in Arjun Pilot, our open source autopilot project in the last year, is this EKF. There's nothing that you would write a paper on per se about it, but as Nick alluded to, it's actually getting this stuff to work for tens of thousands, hundreds of thousands of autopilots out there. Lots of corner cases and kind of things that we found, and how that influenced actually the structure that we use there. A little bit about the overarching system architecture that we have, why that's important, and some words about open source software. So. Let's go to this. This is this very corporate-y slogan that's been invented recently, and actually there's a lot of thought that went into the words, because the thing that we're fundamentally doing is trying to put a lot of aircraft out there in the world and have people use them. And why do they want to use them? Well, probably for a lot of us here, it might just be the joy of flying. That's a good endeavor, research, but the vast majority of the people out there who are flying DJI Phantoms and 3DR Irises are using them to get a picture of themselves and to come to greater understanding of the world around them. This is a vineyard that we do some work at in Northern California. We do a lot of just visual imagery, inspection, and trying to figure out their water usage. So there's any number of applications and reasons why people might want to see their world from above, and I think that's a really powerful concept. So 3DR has been in the news recently. If you type in drone or if you type in 3DR, you'll get all these articles. We just did this round of funding. It's our Series C, so that comes after NB. It's the third round of funding, and it's largely from Qualcomm. And this speaks to kind of where we plan on going, what we plan on doing, and who we plan on hiring. But suffice it to say that the consumer drone market is a real thing, and it's becoming more and more real. Does anyone? This kind of on the next slide. Who here knows what the DJI Phantom is? It's kind of the most popular. Yeah. How many of those do you think DJI sells a month? You have to guess. Any? How many? One order of magnitude off. So they sell about 100,000 of them a month, which is huge. And that's largely driven by this kind of seeing your world from above market. Everyone here knows GoPro. This stat kind of bored me too, but this is essentially the GoPro market. That's like one way to think about it. People who are flying, trying to take pictures. 1 million GoPros a month. That's how many they sell. So that is, a little bit on the business side, which I think actually influences, why costs are being driven down by the consumer market and things like that, and why drones are becoming so huge. So to jump in a little bit about what 3DR does is, I'm sure some of you have seen this before. So this is this autopilot that we produce called the Pixhawk. It's about the third generation of autopilot that we've done. It costs around $200 or $300, and it's pretty sophisticated. It has basically cell phone level processing, probably a little bit less actually, but it actually flies, operates all these different vehicles. Quadcopters are the ones that we see the most of, but it flies planes, all different configurations, boats, rovers. People use it for all different things. And actually, that speaks to a lot of things that had to be figured out about the sensing and the estimation, because when you have an estimator that has to run across all these different vehicles, there's some interesting things that you find out about it. So, very cross-platform, 100% open source software. You can go to github.com/DIY drones and download all the source for everything that's on there. One thing that's interesting, I'll just make one point about where 3DR came from, because I think it's kind of indicative of where we're going to some degree, is 3DR started way over here in 2007 with this market. Now this is really different from how a lot of other autopilot companies started. Proceris, Piccolo, Swift, or Black Swift Black, this is a company out of C. Boulder. They basically started in academia and built high-grade military autopilots, and were kind of exploring that end of the spectrum. 3DR had a totally opposite mentality, which was the first 3DR autopilot was actually built with Lego Mindstorms, and is now in Smithsonian. But way, way, way on the other end of the spectrum. You know, how inexpensive can we build this? Many, many iterations later, we got to the Pixhawk, which is really in a sense a platform. There's tons of companies out there who buy it and use it. And then kind of going forward into more polished, ready-to-fly vehicles. So this is 3DR Iris in 2013, different airframes and different areas, industrial, not just consumer. But it's important to make a little bit of an homage to the roots, which is this very, very much DIY hobbyist area, which is not necessarily an academic community. And I think that's kind of informed where the company has gone. Kind of went over this already, so there's this is just to kind of give a sense of the market size and kind of frame the conversation. 1 in 4 is about how many planes to copters that 3DR sells and other companies sell, which is, I found interesting because having done this work in school and seeing it in academic context, I almost would have thought that would be swapped, but copters are incredibly easy to use, both for research and for consumers. So that's interesting. 116 is the number of developers that are on the ArduPilot open source project, which is, that makes it one of the world's better supported open source robotics projects. It's about double what is on ROS. ROS has a lot of people who, well, the Open Source Robotics Foundation have a lot of professional engineers that work on there, on that. These are largely volunteers, so it's tough to do a apples to apples comparison, but it's a very large robotics project. Okay, so I want to talk a little bit about just this one topic that I thought might be meaty and interesting to understand. And I'll say right at the outset, there's nothing super fundamental difference going on with what we do with state estimation or really control. It's really just getting it to work on tens, hundreds of thousands of vehicles and making sure that it's very robust. So I think the controls analogy is you can think of the performance robustness trade-off, and this is way on the side of robustness. You know, this has to work on such a huge range of vehicles, on people's vehicles that they make out pool noodles, and it also has to be tunable to some degree so that you can actually make it perform well in high performance applications, which lots of people use it for. So I'll talk a little bit about the estimation that we have on board the autopilot. It's probably the most significant development we've had in the last year or so. And it's really vaulted Pixhawk to, you know, basically parity with other professional military autopilots out there in terms of how well it can do position hold or navigation in outdoor settings. Computation limitations is the biggest problem with this. Of course, that will get solved over time, but based on when this was built and the available resources, that wasn't a big problem. Cheap sensors, that will persist to be a problem. If you look at buying accelerometers right now, you can buy them for about $5 for an MPU 6000, or they're about $1,000 if you get something that's temperature compensated, calibrated. And that's really significant. You know, no one no one is really producing well, I'm sure that there are a couple out there, but there's not a significant amount of really good sensors, IMUs, in maybe like the $100 to $200 range. And because of that, we use supplemental sensory information like optical flow to get better state estimates. Most of this work is by this gentleman down here, Paul Briseborough. He was at the ACFR for a while. He was at PAE for 20 years and is a guidance, navigation, and control specialist, and a hugely talented guy. So a lot of what I'm presenting on here is stuff that he's going to be presenting on, keynoting at the Embedded Linux Conference, which is in San Jose in a month. So nothing earth-shattering here. It's a 22-state EKF. It uses the following measurements, estimates the following states that you see there. It is single precision throughout, not double precision. That's a function of the processor on there, which is an ARM M4. And the kind of design constraint is that it had to use about like 10% of the processing power and do predictions at about 400 hertz. That was kind of the spec that was given. 400 hertz is really important for people who are doing high-speed flying, like pylon racing and things like that. In a regular kind of outdoor control setting, path planning, that's not necessary. You can probably knock that down to about 100 hertz. That's what people run down all the time, but it can go up to 400. Again, and I can find a way to circulate these slides. I can post them online if you guys want to have links, but this is all posted online on GitHub, in addition to the MATLAB that generated a lot of this.
Can you tell us about how you estimate the wind and like how many states, how many of those 22 states are about wind?
Yeah, sure. There are two. Excellent. Yeah.
You got some forward model for wind.
Yeah, and it's not incredibly complicated what's going on there. It's pretty basic, so I don't know too much to say there. But yeah,
How
XMY.
sophisticated is the Flemish model for the quadrilateral?
What's that?
Like how sophisticated is your quadrilateral model?
Not.
Because you're
Second order system.
because you're trying to control every other possible.
Exactly, yeah, so that goes back to the performance for less than straight off. It's just basically a black box system. So all this is all kind of another shocking statistic. I'm a little bit more on the control side of things, but so every control loop inside of ArduCopter, which is there's ArduPlane, ArduCopter, ArduRover, every control loop is PID, which is also every control loop in the world. Sorry, controls people. I found that so, but you know, come work at 3DR and you can maybe add an LQR control loop, and then we'll love you. But it's kind of amazing, right? Isn't that interesting? That's how it is, and it's actually just because we need this thing to fly on so many vehicles, and it needs to be. I mean, the tuning is very hard. There's probably about 44, 50 parameters to tune on the control side of it to actually get it to perform well. But it will fly pretty much everything out of the box, and I think it would be very hard to do that with a different control scheme. And it's kind of intuitive. If you've read a little bit about PID, it's kind of intuitive for most people who are, math-wise competent to tune the PID controller. It's easy. Right, so these are all the things that it's looking at. I'll talk a little bit more, then I have some stuff on optical flow. I can talk more after on wind. There are dual sensors. There's actually two gyros as well, but we don't use the second one. There are two IMUs, and there's actually a little common filter that runs to kind of selectively weight one over the other, and they're sampled at different rates, and it's basically to get rid of the ASM. So now we get into kind of the core computation issues. So there was a significant emphasis on making this thing efficient because of the limitations of the processor, right? Something that you don't really think about too much in MATLAB land, but was very, very important for this. Additionally, ArduPilot runs on a single thread. That's not great, it's kind of a legacy thing, but that was kind of the hand that was dealt. That means that every one of your computations, from sampling sensors to estimation to control, that whole loop is running basically sequentially. All the interrupts come in on that same frame. And we need to do predictions at about 400 hertz. And this pretty much means that we have to complete this prediction in about 1300 microseconds in order to take up less than 50% of the frame. So we have subject sometimes to control. So estimate, sample, estimate, control over and over again, and that's what you get. There's another kind of odd thing that was found that, and this is just speaks to how the implementation of this was done, but actually one way of implementing this is to generate C from MATLAB. You use the MATLAB compiler, but it couldn't do this computation. It couldn't do the 22 state generation of C code. Possible that a faster computer or bigger computer could do it now, but there was actually a lot of simplifications that were done to reduce this from a bunch of matrix operations and exploit sparsity to do sequential scale operations. I'll talk a little bit about that here. So, solution number one to solving the computation overhead is that basically all of the equations for the covariance prediction are implemented as scalar equations. There's no vector matrix map in there. That's also surprising, but that's actually because there's just no library that we could import. We didn't want to build a library for leveraging sparsity. It's definitely something that we should look into in the future for doing vector matrix operations. But if you're doing this on even a moderately powered Linux CPU, you would probably install something like Eigen. I'm sure SciPy has some tools for doing this. There's any number of great packages, but that wasn't available on this. This is a real-time embedded system that just has nothing on it. It runs on an operating system called NutX, which is built by a guy named Greg Nutt. So, there you have it. And that was kind of like the hand that was dealt. In addition, the runtime of this whole about 2600 microsecond frame is that there are a bunch of different batched operations that happen. So you think that you would sample all the sensors at once, but they actually get sampled sequentially. And that's just to make sure that you don't have frame overruns, so you can guarantee that that everything will finish within that window, because as soon as you start having frame overruns, as soon as you say, okay, I'm going to read all these sensors and I'm out of time, then you miss a whole control predict cycle, and that would be very bad. That's a copter crashing problem. So there's many things that we do inside to say, okay, this data actually hasn't changed much, so we're not going to piece it into that. That's one thing that happens. There are some areas where we exploit the sparsity that is going on. It's big covariance matrix and it's largely built with zeros, so there's lots of computations that we don't have to do because this is really straightforward. If you were using a package like SciPy or Eigen, it would just do this for you, but that has to be explicitly done rather than just figured out by some math package. One big problem with doing particularly this sequential kind of sampling, so read gyro X, read gyro Y, read gyro Z, is that in those time gaps, you can develop things like coning and sculling errors, coning on the accelerometer and sculling on the gyroscope. That's the error that you accumulate over that window. So that can cause huge stability problems for your filter. And there's a whole bunch of, this is caught in the end by a bunch of consistency checks. You look at the innovation sequence and you make sure that it's not blowing up. But you have to do some things to guarantee that when you actually sample that it happens within a reasonable amount of time, and you have to look at how much things are changing to know that. There are also some jitter issues associated with the variability with when sensor information comes in. So because the scheduler that runs on top of this isn't exactly real time, and we can't exactly guarantee that we're going to collect a sample at exactly precisely this moment. This is, by the way, a problem on any system that you don't have really hard real-time constraints. These all are problems that need to be mitigated. And it's very hard because the way that these problems are manifested is all of a sudden you have very bad state estimates, and it's very hard to figure out why sometimes. And it could be because you started sampling one particular sensor too slow, or another sensor, the gaps between when you were reading inputs increased for some reason. So these are all problems that would be solved on a much more much larger system. But again, if you want to do this on a very inexpensive micro and sell an autopilot for $200 in 2014, then you don't have all of that available to you.
These are all going to be replaced with Snapdragon?
That's a great question. Great Qualcomm product. I love the Snapdragon. Interesting. Yes. Just in case there was someone who was recording, right? One of the interesting things, I went to CES for the first time this year. Has anyone ever been there before in Vegas? It's nuts. It's actually, I would probably not go again. But in the Qualcomm booth, and this was covered on The Verge and places like that, they had this quadcopter that was flying. And it was actually using this companion software stack called PX4. If you read on, this kind of drives our marketing people insane, but if you read on here, it says Pixar 3DR PX4. PX4 is this open source project out of ETHR. Also very well supported. It is BSD licensed, as opposed to our software, which is GPL licensed. Big kind of religious debate as to whether to use one or the other, but for large companies, kind of the gist of it, for large companies like Qualcomm, using BSD software is potentially just opens them up to less legalities and less problems. So they run PX4, and they actually have inside the Snapdragon a little DSP. I forget what clock speed it runs at, but they run all of the control, sensing estimation control in this little DSP, and they have this giant quad core system to do vision, to do whatever else. And yeah, I wouldn't be surprised if I saw it in the future with the R5. It's a great
Is there
show.
hope for $200?
Yes.
They're close, right?
Yeah, it definitely is. So like what the cost of materials on a cell phone is like, around $200, and they're being used on cell phones. So it's something. I think they're probably selling to Apple for probably like $50, if I had to guess. And they could be a lot less. So yeah, great question. This is kind of so all of that problem before that I was describing with consistency checks. Those are like really having to do with the fact that we want to make a very inexpensive autopilot, and it's using this micro, and it's fundamentally single threaded, and kind of all these problems that you probably hear and are like, yeah, just get a faster computer. And I totally get that. But this is a problem that actually doesn't necessarily go away with a faster computer, and this is bad sensor data. So until someone makes a really good IMU that's say $50, which there just isn't a great market for that right now. They're more like a $1, $2 IMUs that go inside cell phones. You're going to have this problem of not great data, and you have to understand how to deal with that. There are also, one of the goals of this project is to have this autopilot work on all different kinds of vehicles. So getting this thing to work on 95% of vehicles is not a problem. It's all about the corner cases where it doesn't work. It's all about putting it on a rover that has a ton of vibration, or a plane where the propeller is nicked or something like that. And this is solved with military autopilots by sampling faster. Some probably fairly intelligent DSP, but we have to do some kind of different tricks here, some similar tricks, but some different tricks to deal with these problems that I've listed here. So IMU and gyro offsets, IMU aliasing, GPS glitches, barometer drift, all sorts of disturbances. Magnetometers are hugely problematic to get good readings out of them. The placement of the magnetometer matters greatly. Placement of the barometer matters greatly. Especially for copters that are generating a ton of dynamic air pressure. It's kind of a sample of the different kinds of vehicles that RG Pilot has put inside. It takes about if you're a competent developer, it takes about an hour to autonomize a vehicle. I used to use the Piccolo Autopilot, which is this military grade one. It was a lot longer than an hour to get to work on a vehicle. Various solutions, so explicit estimation of IMU biases. We actually do an auto-tune routine where, if you're flying around just gently, which is how most people fly, you actually don't excite all the axes enough to really fully identify what the biases are in your IMU. So we go through a calibration routine where it does very hard step inputs and roll and pitch and yaw to estimate those. And you can turn that on at the beginning of a flight or turn it off. There's all sorts of consistency checks on innovations to make sure that they're not blowing up for any of the reasons that I mentioned earlier, having to do with low computation or having to do with bad sensor data. Those would be manifested in the same way. There's timeouts associated with if you don't have GPS for a certain amount of time, they're kind of obvious things to do. There's a bunch of logic to recovery from GPS glitches, which is hugely problematic. Even with nice GPSs like uBlocks, use the uBlock 7 series and 8 series, pretty high quality GPSs, still all sorts of glitches, which is, it's randomly jumps 100 meters away. And you have to do things like, well, did my copter actually teleport 100 meters away? Probably not. All sorts of alias detection. This mainly happens through variable sampling of our 2 accelerometers. Even that sometimes isn't enough. And then this kind of intelligent weighting of both the accelerometers, where we have a little filter that runs and kind of gives higher weight to the one that has the lower innovation sequence. I'm sure the audio will play, but this is a little bit of a legacy video, but this is kind of what things used to look like when we didn't understand these problems, or when people working on the project, largely that hobbyist group, didn't understand what was going on. See if the audio actually plays. Hold on. It's really working out in the audio. I'd be able to just do this actually. So that was actually, so that was actually a problem because the people who were writing this at the time maybe weren't robotics students at MIT and just used GPS measurements directly, the direct observation of GPS, which is hugely problematic. There's many very simple things you can do to get away from that, but there's also, again, corner cases. So what happens when you initialize your GPS if it's warming up and it gets a measurement that's, say, 10 meters away from where you are? How do you discriminate that from where you actually are? How quickly do you allow the new GPS measurements to converge? Figuring out your home location is actually very, very important. How long do you make a user sit there and wait as the GPS acquires? You can go to YouTube and look at like flyaway clubs where people's aircraft go far away. This is almost always because the GPS got a bad initialization on startup. Because this is a consumer product, you don't want to tell someone to wait until the HTOP goes below a certain number, or the HTOP or PDOP aren't valid metrics for whatever reason, and there's a home location that happens to be, at 0, 0 instead of, right out here. And, you get these problems. We figured out how to check the 0, 0. It doesn't go to 0, 0 anymore, so that's it. I'll just mention briefly, there's quite a bit of work that gets done. There's quite a bit of work that we actually do with this company, SwiftNav. This is an RTK GPS that's around $1,000. It's a full RTK solution. And, I don't have any great plots because I can just tell you in words. It can keep about, once it acquires, it can station keep to about a 3 centimeter box outside. That's like 3 sigma bound. And this is very ecstatic Stanford graduate student. So this is it's very possible to get good. And this is, I think, also a story about most of the problems are really about estimation. The control part is also hard in the corner cases if you're trying to do like things you have here, where you're trying to fly through windows, where you're trying to perch. Then it's very important. But for station keeping things like this, if you're not trying to fly through windows, if you're not trying to do these highly dynamic maneuvers, and most of the problems, at least on ArchiPod in this project, have to do with estimation. That's where 90% of what it takes to get to this comes from. It's good estimation.
How much wind could you tolerate?
That vehicle, this is a 3DR Iris, can fly. Probably hear it. This is probably about 20 miles an hour upwind, like 8 meters per second. Some of our planes, the Delta Wings in particular, can fly in really high winds, like 40, 50 miles an hour. If anyone's familiar with, we just had a great talk by Eric Frew, professor at CU Boulder. He flies ArchiPilot fixed-wing aircraft into the rear of tornadoes to study the phenomena that goes on there. So that's 80, 90 miles an hour wind for fixed-wing aircraft. So that's like a carbon fiber, very strong delta. Most copters you wouldn't fly in much more than the conditions you see here, which is about 20 miles an hour wind, which is still pretty gusty. That's what it's like every day in Berkeley. So I mentioned this kind of at the top, and I'll briefly go over it. There's also this sensor that we produce called the PX4 flow sensor. Again, it kind of has this ETH heritage. And the main reasons why we want to have this optical flow plus range finding plus ultrasonic range finding, it can be combined with a single point LiDAR as well, is that people want to be able to land very accurately. That's pretty much the design driver for why you want to have this. There's also indoor station keeping, which is I think way more interesting from a research point of view, and probably more what goes on in academia, but for consumer applications, being able to land very accurately, not flip on landing, hugely important to have a good altitude estimate. There's nothing hugely fundamental going on here. The measurements from the optical flow sensor are going into the EKF at 10 hertz, that's the observation rate. And yeah, you kind of have this dual observability problem if the velocity is zero, non-zero, excuse me, then you can tell what your height is, and then vice versa. So you need to sort of one to the other. And you can actually get pretty decent, I don't have any videos of the landing. Oh wait, I'll mention, they're basically the problems with this are the sensor is bad, right? Like the focal length in particular of the lens isn't characterized well. If you were doing this in a kind of a research setting, again, you would be taking pictures of checkerboards every single time and calibrating your lens, but we don't do that. So you need to estimate those or deal with that uncertainty incorporated into your filter, whatever. So here's kind of how this looks, and this is actually not totally a success story, because what you'll notice is that the gentleman will walk under the vehicle and it will kind of follow him. So this is actually a big problem that comes out of this consumer space, because guess what? People fly over other people all the time. So if you're going to, which is not safe in general, especially at this altitude, but you can kind of see the aircraft travel along. So most of the scene is stationary except for the person walking underneath, and the aircraft kind of goes along with them. Landing on grass is also a big challenge, especially if the grass is kind of moving a little bit. Things like laser rangefinder make this a lot better. You can get a pretty good laser rangefinder for about $100 to $400 now. We've integrated those as well, mainly as kind of like research projects. And of course, there's expensive laser rangefinders that have existed for a while. The vehicle that maybe you guys have seen, the DJI Inspire 1, it's like kind of a prosumer level aircraft. It has a dual ultrasonic rangefinder. It uses both of them are kind of pointed out like this, and that's how it does very, very good altitude hold. So just a bit of a wrap up of this section. What we figured out through doing this kind of exercise and where we think things are going is that we made some very, very big gains in the performance of the EKF and this is from about, it was, when we tried to do we didn't reduce it to scalar operations. It was taking up about 60% of the processor, which is unacceptable, and now it's down to about 8% of the processor. That was just through all the efficiency gaining operations that I mentioned before. There are definitely stability challenges, particularly with single precision math, so I think reasonable to think that the next generation of autopilots will do the thing that exists in many embedded systems, which is double precision, more cores than one, multi-threaded. And I think the biggest take home from doing this is actually getting ECAT to a place where it was, could work 90, even 95% of the time. It wasn't very hard. That was about that gentleman I mentioned, Paul, who's the GNC specialist who's been implementing ECAS his whole life. It took him, I'd say, about 2 months of prototyping to do that. It's taken about a year to figure out all the corner cases, and particularly the state machine that runs on top of everything. So when are you landed? What is landing? If the user isn't explicitly pressing a land button. What do you do if you have a very bad GPS glitch? what are the fail-safe conditions that you go into, and what does the EKF do in those scenarios? What happens if you're pretty sure that one IMU is bad because it's $5 and they go bad all the time? So it's those kind of corner cases, and it's actually the state machine that that switches between one thing or another and does that in a safe way for the EKF. That really is what drove this to be a useful and an autopilot that works on something like 200,000 vehicles out there, 200,000 vehicles minus. There's
Can I just ask, and
Yeah.
so why is it PKF? And which part, you say you got a trivial, works for any vehicle, linear model probably with the plant. I mean, or when some of your sensors on here, or where's the linear coming in that you're touch the bone with?
Yeah, so there are some nonlinearities with the plant. There are a few. It's not totally a straightforward model, particularly with plane. Talker not so much, but with plane, yes.
You
and with-
please tell what, never plane model, you have.
Yeah. Oh, yeah. And rover, non-holonomic vehicle.
Okay.
So the observation models are very simple in most cases. There are some more fancy things going on with the magnetometer, scaling that appropriately. So there are a few areas where it is nonlinear, but yeah, your point is well taken. I think actually there's this competition that happens every year called the Outback Challenge, where people go fly UAVs and they try and do this task. They try and go find a lost person. One team that did quite well this year ran a UKF on ArduPilot. They implemented their own. It's also open source, and it did quite well. And it used very little computation. They had a ton of very they're kind of dynamics gurus from the ACFR, from Australian Center for Field Robotics, and they had all this complex nonlinear dynamics because of how you sample it essentially with a UKF. They were able to do it on this processor fairly cheaply. So I think that that's definitely a direction we can go in. There's a very interesting little 9-state gimbal estimator that the same engineer Paul is working on as well, which I'll just mention here, and it's worth checking out as well if you're interested. More nonlinearity is associated with that particular sensor. Having very stable gimbals is becoming more and more the thing in the consumer space. Again, gimbal is one of these things that up until probably 2014, it would be very hard to get a good camera gimbal for less than a couple $1,000s, and now it's becoming more and more possible to do that. And that's basically because of really good estimation. Same cheap sensors, same story. To kind of go to a totally, and I'm happy to go back to that and answer whatever other questions about wind estimation you guys might have. But I want to kind of pop up a level and talk a little bit more about what 3DR sees as the future for us, for the platform that we want to build on, where we think the consumer drone market is going, and some comments about the system architecture choices that have been made here, just because I think it's kind of interesting, and why not talk about these things a little bit. So I'll start with saying that so 3DR I mentioned does a ton of open source software. Not everything we produce is open, but a lot of it is. And I think one revelation has been there are really many different meanings of open. It's kind of a not exactly specific term. You can kind of group them like this. Sometimes people actually use the term open to mean that they've created some really good documentation for how to use their API. That sometimes means very open. They have an open platform. Sony actually, Sony cameras say that they have an open platform for development. They don't have open source anything. They just have an API and related documentation. And then open source is all these different licensing schemes, and you can choose them based on different legal issues. I'd say the biggest one is BSD versus GPL. GPL has this very viral component to it, which says that anything that it touches must also be open source. Our developer team lead named Andrew Tridgell, he is the inventor of Samba, he's the inventor of rsync, he's the Git in Git. He also writes the GPL standard. So lots of our software is GPL as a result. This question gets asked a lot by maybe not people here necessarily, but it's definitely a question that, say, investors would ask, and it's kind of worth thinking about, which is, how in the world do you have a company that makes money off of open source software? Why would you give things away for free? It's actually, I think, really worth thinking about because, there's all different open source software around us, actually, for what is in an iPhone, this is quite open, BSD license. And I think the main reason is, especially when you're a small company, you really want to drive platform engagement. You want more developers to use it, and people who are consumers might not necessarily care about it, but if there's a game to be played for the number of roboticists out there in the world, the number of developers, I think that most of them would be happy knowing that they're not locked into one specific platform. If they build tools in one area, they can transfer them somewhere else, and that their software will live on beyond a particular project. There's also something to be said for quality, and this goes back to the platform adoption. So every time we roll a release of, say, Argent Copter, there's probably something like 500 to 1,000 people out in the world who are top-notch, doing pilots who go and test it. And that's because, not only test it, but I actually make pull requests in GitHub to contribute back bugs, whatever they see. That's hugely important. That allows a company like 3DR that's very small, about 300 employees, to move very, very fast. And not all those employees are engineers. It's about 40 or 50 engineers right now. I guess fundamentally also is, we like to share. I think it's not too different what happens here. You publish a paper. This is a culture fundamentally of taking your ideas and sharing them with the world. And I think that's really important. And that's why a lot of people work at 3DR. There's actually many different models for how this works, and of course it's like fairly nuanced like anything, but the thing closest to what we do is this open core model where it kicks off. The autopilot at the center of the system is completely open source, GPL free. There's any number of companion computers that people attach to this. This is like every startup company on Kickstarter that's doing Visual Follow Me or something like that. We'll run a Raspberry Pi, Beagle Black, and Odroid, one of these kind of high-powered CPUs. And then I write some closed source things on there. There's any number of ground control stations. Because this is actually kind of a fairly user-facing component of the system, we maintain pretty tight control over things like Droid Planner or Tower. These are mobile ground stations. And then I'll talk a little bit more about what goes on the web, because I think that that's becoming increasingly important in that. It's kind of another area you can kind of imagine in these different layers. So another perspective on it is, you have kind of like any stack diagram. You have your operating system. One level above that is the primary flight controller, which is really the embedded system. It might be directed by any number of onboard computers, off-board computers, and then web applications. It is actually possible, I'll show a slide in the 5 internet, it's actually possible to command a 3DR drone that implements MATLink, Open Communication Standard, over the web. It is technologically possible to do that. I'll kind of give a little demonstration of what that looks like. These are kind of, if you're familiar with the autopilot world and the Argent Pilot world, of what goes on inside of Argent Pilot right now. Maybe this is a little detailed, but this is the operating system that I mentioned before. These are the two different software stacks, GPL, BSD, any number of kind of supported projects that all sorts of people are running. This all runs on this open communication standard called MATLink, which is actually also implemented by Parrot, who is the world's second largest drone producer to DJI. They make Evolve and they make the AR drone. 3DR has kind of a companion stack over here of some closed and some closable applications. So there are projects to make co-pilots internally, of course. There is ground control stations, the one that we make right now for Android that is free and available is Tower. And I'll talk a little bit about this drone kit, drone hub, drone share thing over here. This is where ROS would live. Most of the time it's something that you're not running on the primary flight controller or the embedded device. You're running it kind of off-board on a higher powered computer, or off-board over a communication link over a network on a ground station. You can kind of imagine, I put App Store in quotes up there because it's like a really loaded term, but you can kind of imagine that people might want to actually develop applications on this platform in the future. People do it now all the time, and it's definitely getting bigger. And the way I like to think about it is there's companies who are maybe interested in developing on this. Let's say that they're size like N. There's companies that are interested in developing, writing, say, in Python on a computer that talks to this, that's talking to higher level sensors. That's probably 10 N. And then there's companies that just want to deal with the data associated with drones through some web interface and write some slick application for visualizing, for content posting, whatever. That's got to be way bigger, 100 or 1,000 N. Because the burden of development, because of how much you need to know about the embedded system, is just vastly different scales. So this hasn't been really publicly talked about much. If you dig through our website, you can find it, but there's actually an API that is in the works that will be officially announced at this Embedded Linux conference, but it's called DroneKit, marketing name, and it's actually very useful and very incredible, and it's somewhat parallel and ROS to some ways, but it's really for people who want to develop applications on this, and it's really for businesses mainly. But the important things to note about it is that it's on the website, it's a full REST API, and what it really allows you to do is not have to understand malware, not understand this raw data stream from off the vehicle, which is really high ask for people who are just web developers. If you just want to query some database and get some return as to the state of the vehicle or all of its log files or whatever, you don't want to have to do that in Matlab, which is kind of this secure communication standard developed at ETH. You want to use something really common. You can view it also as a central data broker. There's all of our log files get uploaded to the web. I'll show you the portal to that in a second. And this is a way of accessing them. And it doesn't yet support these things, but you could imagine it supporting, it'd be very easy for it to support streaming services. So this would be like streaming information live to the web, actually in real time as opposed to just after post-flight. And then to speak to the App Store model, you can imagine also a bunch of interoperating applications that would use it. So the word homogeneous is meant to imply the fact that you can actually write an application that would run on a computer that sits on the aircraft, you can write it on the ground station, you can write it on the web, and you'll be using the same API, which is a very powerful concept for people. I think also particularly researchers who want to maybe prototype something where the development burden is lower, and then once they need higher performance, actually move it on board the aircraft or actually into the primary flight controller. So there's all different implementations here. There is an Android implementation, a Python implementation. There is a website to it, and this is really the only bit that 3DR, just kind of for mapping information's sake, this is really the only thing that 3DR keeps closed, which is user data. It's log files. Let's see if I can bring this up here. So, let's see. So this is a site called DroneShare, which is it's up right now, and you can go to anywhere in the world. These little things represent everyone who's flying a 3DR vehicle around the world right now. If I'm going to use the internet, which I think I am. You can click on them, you can query what they're doing. It looks like this person probably just turned, it's because I don't have the internet. So that's the slide where I took some screen captures of it. You can query any of those particular flights. You can look at the mission. This is what you would see if I were actually connected. You can look at the mission that they're flying. You can look at the speed and all sorts of statistics. This is actually like really analogous to these kind of social sharing sites like Runkeeper or Strava or something like that. So it's it's called DroneShare for a reason. It's primarily social. Although I think the implications of having all this data on the web are far bigger than just social. And this is the type of data that would be at your access if you were a company that say wanted to interact with this, or you wanted to actually upload all of your data from your vehicles to the web and do analysis with it. So there's these automated reports that are produced. This is a little fuzzy, but this is saying that there's a GPS glitch error. I wouldn't call it machine learning, although that would be very possible to do here, but there's statistics that are applied to this to say like, yeah, this is out of an acceptable range, or just hard limits that say, if your HTOP went above this amount, then show an error. Actually, all of our support, 3DR support is triaged through this, so you have a problem with your vehicle, you press a button, it sends this log up to DroneShare over this REST API, it creates a Zendesk support ticket, and it contacts them in support, and then they pick up the phone and call you. It certainly makes the support people really happy. There's tons of things that, this is I think really exciting. There's tons of things that you can do with this this log data. Does anyone want to venture to guess how many hours of log data exist on DroneShare? There's about maybe 2,000 users on there right now. Thoughts? 150,000. Pretty close. There's about 400,000 hours of log data, which is a huge repository.
How much of this is sitting on the ground wondering why?
No, No, it's probably, most of it got removed. I don't think that's reflected in the 400,000 number. It was not, it was about 1% there. It's, you know, some portion of it, but not all of it. So, I know that you guys have things to go to, so I'll just wrap up quickly here. Yeah, I think it's important to mention that you know, open source software for 3DR in general is really just a development model. It's a way of doing business. It's a way of attracting people to your platform, and it's not a business model. I think that's something that's actually often conflated about the two. That's not true. It's not a way of doing business. It's a way of doing development. And there's tons of companies out there, very successful ones like Apple and Google and Red Hat that do it all the time to great effect. 3DR is open, mostly this open core model, and at least we think that the access to this data that I just showed is going to be hugely important in the future. Of course, we're going to be working on new autopilots. That goes without saying. Maybe they'll have Qualcomm chips in them. Remains to be seen. We'll be working on new consumer products. We'll be working on new industrial products. Definitely working on this concept of open development. Part of the reason why I'm here is that I really am excited by the idea of engaging academia more. There's historically pretty low contributions from the academic community, and I get it, because like, what's the value to you contributing to this project? You're trying to do theses and things like that. But thinking about ways to make that path smoother, I think Ross does this really well. Working on things like that, and yeah, I think 3DR, a lot of the money that we raised is going towards higher education. 3DR has about 20 or so software engineers now, and it will probably double very soon. And worth mentioning as well. We do all the typical robotics things. I talked about estimation a little bit. There's some controls problems to work on. Lots of signal processing. Lots of electrical engineering. Lots of aerospace engineering. Yeah, I'll conclude with that kind of hokey slogan that I put at the beginning, just to bring it back to the start. But thanks a lot for your attention. I really enjoyed being here, and I hope to get to chat with you guys throughout the day. It's people, I want to be respectful of your time here. Questions? Yeah. Oh yeah, there's Yep.
So you showed the video and you went to SwiftNav offboard. You got some awesome. You mentioned that backend and 2 centimeters.
Yep.
For satellite GPS, is that a meter, or what range do you?
For just like conventional GPS. Yeah, so I quoted like the 3 sigma bound, which was the 3 centimeter number I gave you for the SwiftNav. For the U-blocks, it's something more on the order of 90 centimeters to a meter. And it's really about like reducing. It's funny how you would incorporate glitches into that, and how you incorporate the conditions. But if you were to, in practice, if you were just to use it, something like a meter. But of course, we do station keeping way tighter than a meter because we're doing inertial navigation. It's not just GPS navigation. Measurements of many.
You guys have any interesting processes for finding the 5% of car cases that really burn you? Is it all based on some guy sends a bug report in and you look at his log file, or you guys have?
Yeah.
How do you do that? That seems really hard.
Yeah, that's a great question. So part of it is brute force, for sure. And there's some corner cases that I think you can only really find through some random person tried to make a copter out of pool noodles, and this is the vibration that they got that on LSAW. There's a site I can pull up after this called autotest.dlydruns.com. Again, that lead developer, Andrew Tritchell, who's probably got to be one of the world's most preeminent software developers. He's the guy who wrote Samba, which is a very important piece of software. He is really invested in this idea of testing. So every commit to Git kicks off a series of simulated vehicles. So software in the loop is the short answer to your question, but very high fidelity nonlinear models, not just point mass models. We found a very nasty bug using this flight gear simulator actually, where the orbit radius that a plane could hold at something like above 20,000 feet wasn't that tight because of the air density and all these kind of crazy problems. That would be actually the corner case that'd be very hard to test because not many drone users fly at 20,000 feet. But the software did, and we were able to kind of catch it at this macro level and say, oh, the cross-track error on this. We were expecting it to be below whatever, and it was huge. Why was that? And it turned out to be this great density thing.
Can't let you get away with asking about what the new regulations are going to do and what your view on the LEAP proposed rule is.
Thought that was going to be a wind estimation question. I have this one. I have to answer this one all the time, so I have this one down. But yeah, so you guys might know there was this FAA like leaked document about regulations, actually incredibly permissive, kind of shockingly so for the FAA. That's not been exactly the most forward-thinking group. You know, it's kind of a mixed bag because 3DR has done pretty well because we've kind of figured out how to sell our product. We ship from Mexico. It's open source software, so like if you bundle it, then it actually technically gets loaded on the autopilot after the customer gets it. So this thing is electronics, plus the software is a missile in certain contexts. So those things diverge and then converge at the person's house, so we don't have any liability for it. And there's all sorts of like weird things like that. And I think that opening up the space in one sense drives the platform forward, or drives, sorry, not the platform, but the industry forward, and which is going to make more competition for us necessarily. One particular point that I'll draw out from that is they've opened up a lot of the commercial applications, which, you know, to be honest, people have been doing quite a bit of, especially abroad. And the fact that they're now more open in the US, I think, is going to really drive the industry. So companies that were big and previously scared of getting into drone operation, John Deere, any construction company, biggest industries in the world by like dollars, agriculture and construction. Super conservative companies, they don't want to touch drones, they think it's remotely, you know, regulatory, problematic, are probably going to get into this space a lot more, either directly or through small companies that will be.
Your open log of people's flights doesn't discriminate, everybody who left their data.
Yeah, you know, we think about that quite a bit because it would be very easy. I could write a query right now to say, like, show me all the logs of people who flew away this far away and this high. It's a very DJI kind of move to explicitly prohibit that, so they have explicit geofences that you can't turn off. We, on the other hand, have geofences and stern warnings, but you can go turn them off if you want to. But we protect this data. We have a privacy policy associated with it. It does get subpoenaed, and we adhere to that when it does, if the drone was being used for illegal means. But you know, for the most part, it's like any other user data. You know, if you ever looked in an Android phone, it knows where you are at all times. It'll show you a map of it. It's pretty scary. So they're very similar privacy policies.
So last semester, we had a talk by Steve Lapal. He's working, or he was working at Oculus Systems. Basically on same problem, the same estimation problem, like filtering.
With the tracking.
Tracking the state, right? So, are you guys think, I mean, you take your autopilot and you strip down the control part.
Yeah.
Estimate. Looks like we have like many more applications for it, not just driving things so much.
Yeah, they're really similar, but one big driver for them is incredibly low latency, which is also, you know, I kind of talked about, is also a driver for us to a certain point, but they want to get this head tracking below something like 10 milliseconds so that you really don't notice any of the lag. That's actually the loop time. So the estimation, the control is all, you know, the computer running the physics engine, so that's pretty quick. It's not exactly the same problem, but yeah, I could see them being interested in this, but they're really trying to sell this consumer product. I don't know how interested they are in using open source software per se.
Yeah, and just I think in general, right?
Yeah.
It might be like, I don't know, like Atlas could use like a state estimator with Flutter.
Yeah. People use these all the time just as loggers, as data loggers, because they're very, you know, if you want to go, the closest comparable product to it, I think, is something like a Vector Nav IMU. Have you guys seen those before? Like pretty high quality GPS plus accelerometer. I think the cheapest one is around $1,000 now. So if you want to do pretty good state estimation for $200 and have like a nice Android tablet that talks to it and logs it and pumps it to the web and allows you to click one button to share it to Facebook, so you say, oh, check out this experiment I just did and look at how good the state estimation is. You know, that you get all that stuff for free. for, over $200. And so a lot of employees say for that reason, it's not good.
It seems like there's this divide between the DIY sort of hobby community and your commercial products.
Yep.
And having the flight controller work for both of them.
Yeah.
Do you feel that it would be worthwhile to have a version of the controller that's more tailored to some of the commercial products that you have control over, that you can do SysID on and things like that, to make a controller that doesn't just work for everything sort of well, but works for your main products very well?
Yeah, also a great question. So that's essentially what Red Hat does, because they take a version of Linux. But what Red Hat sells and why they're a Fortune 100 or 500 companies, they sell peace of mind to big companies. They take the scary thing, Linux, and they wrap it in a nice package, and they say that they're going to support it for 10 years, and they do a ton of reliability testing on it, and then they sell it and people buy it. And we could do a very similar thing, and we effectively do. So we fork ArchiePilot, and we develop it in forks, and then when we release products, we merge. So the only stipulation is that you release your source. You can just release it as a tarball. You don't even have to like put it on GitHub or anything. So we develop in a very separate from the community a highly maintained fork, very reliable, and then when we're done, we merge it back with master.
Because I mean, like you said, the PID controller is being used everywhere in the world, and it's 200 years old.
Yeah.
And because it works well for everything, but because you have control over your product, it seems like developing a hand to or like a tailored to your specific iris, for example.
Yeah.
There are benefits behind there.
Yeah, definitely. And we accomplish that basically through really good param files, really good games for just our vehicles. So that's essentially how it's accomplished. We have 44 very well-tuned games for just our vehicles. But in the future, I think it definitely would make sense for us to at least explore the option of breaking off and having our own kind of maintained version of it that gets released and whatever. But it's more in the community to fold it back in. Part of the problem with doing that is it's not very software architecture-wise. It's not very modular. It's very hard to change something about the controller and not change like a big portion of the system. So there's some architectural stuff that has to get done as well to make that work.
So other than the license, what's the difference between PX4 and ArchiePilot?
ArchiePilot's much better. It's yeah. So it actually ties into what you were just asking about. So PX4 is way more modular, and it's developed for university use. And if you want to plug in your controller, it's very easy to do that, and it's very easy to see how to do it. It's pretty well documented for doing those sorts of things. Like I want to plug in my controller. Whereas ArchiePilot is way more robust and tested. Might be harder to develop on, but if you actually are a company and you want to go put this in your aircraft and have it work and just be pretty good, that's like kind of the main difference. So more tested, more developed, more modular, and more academic. But those two projects are merging pretty quickly. I would say that distinction might not be so true in say 6 months. Was there another question over here?
Yeah, it's like, you said you use PID in every single control. So is the main impediment to using something more sophisticated that you have poor SSA estimation, you just don't have any idea of the model, of the plant model, what you're going to be flying on, or you just do well enough with PID?
Yeah, so it's a combination of all those. We do well enough with PID. The EKF was something that our state estimation used to be pretty poor until about 6 months ago, and now that it's better, now we can think about actually doing control much better because the estimation's better. I'd say the biggest reason why we don't do it is in the community, at least, who's really the original maintainer of this. They don't necessarily have a competency in that area, and this is exactly the areas that 3DR is hiring in. Yeah, it's really because PID just works really well for this broad range of scenarios and is tunable. And if you're going to put a plant model in there, even if it's a model plus some parameterized uncertainty, you really have to understand how that's working very well and do really good modeling in order for that to actually produce an end result that's better. Does that kind of make sense?
Maybe break for food. Thank you
Yeah.
very much.